Okay, I think we're going to go ahead and get started. Welcome, everyone. We're talking about hydrology and hydraulics for non-engineers today. This is Ceil Strauss, and I'm the state floodplain manager working statewide with communities on their floodplain regulations and interpreting things and helping be a go-between with FEMA. And Gary Bennett, who's newer in our floodplain program, is going to be helping with watching the chat and making sure that the logistics are going okay. And then, Anne, how about you introduce yourself?
Hi, I'm Anne Toftegaard. I'm a floodplain engineer in the DNR'S floodplain mapping and modeling group. And I primarily work on updating maps in Minnesota for FEMA flood maps. And I was telling Ceil I had a good day today because I made it into the office despite 14 inches of snow in Duluth over the weekend. So
Thanks there. Yeah, and I have to mention that we're in 3 very different locations around the state between me and Gary and Anne. So it'll be hopefully all the logistics go well today. But I'm going to turn off my camera and start presenting just to keep the bandwidth better here. And so we are talking about hydrology and hydraulics today. We'll go over a little bit of terminology and some mapping background, but then we'll be jumping into the hydrology methods and hydraulics methods, talk a little bit about what's steady versus unsteady models and 1D versus 2D models. And then we'll talk at the end about how hydrology and hydraulics are shown in the FEMA mapping and a little bit of resources. Now, we will have time at the end where we'll stay online as long as there's people asking questions. We'll turn off the recording at the end. The other thing I wanted to mention is people often want to know if we're going to be sharing the slides. We will prepare the slides as a PDF and share them afterwards. So be aware that we do plan to do that. So our level of detail for this presentation today, we're going to be somewhere between these 2 levels of detail. On the left, you can see this nice complicated equation that's part of the background for one of the modeling techniques that we use frequently. And we're not going to get into a lot of math and formulas like you might if you were taking an engineering class on these topics. On the other hand, we're not going to be so basic as to just say water goes downhill, as you can see in that nice waterfall picture we've got there. We're going to be somewhere in between, hopefully keeping things in plain language for folks and hopefully useful enough that it doesn't seem too basic. Now remember that our supporting data is for the FEMA mapping that we have. And the main mapped areas, the high-risk areas that we're talking about on the FEMA maps are referred to as the Zone A's of some type. Zone AE, E meaning the elevations on the FEMA map, or some of the older maps, they have A with a number behind it. Those are the areas where we have more detailed modeling. Some of the models that we're talking about that do get into more detail will be in those AE or those numbered A zones. Zone A or approximate A zones are areas where in the past there was basically no supporting data, very little supporting data. Our more recent modeling and mapping updates, we have a lot more great background information that we'll be talking about the kinds of information that we have and the kind of modeling that we do. The Zone X are the areas where either it's lower risk and there is no mapping, or it could be, say, the 500-year areas. So those shaded Zone X areas, we may have data for, depending on the circumstance. And some of our other trainings, we get into more detail about some of these different types of Zone X. Statewide, we have a lot of the A zone where we don't have the detailed supporting models and data. We do have a fair amount of detailed area, those red areas, especially in the metro and along the major rivers, or areas where we have a greater flood risk. We tend to have the effort where we got more data and we have the detailed supporting data. When we do have the detailed modeling, they will have several flood frequencies, and the 100-year or the 1% annual chance flood elevation is what we're regulating and what's used to determine whether someone must get flood insurance or not. But when they're doing the modeling, they're also calculating what are the levels of flow and how high does that water get for a 10-year flood or the 10% annual chance flood, a 50-year flood or the 2% annual chance flood, and the 500-year flood, which we also call the 0.2% annual chance flood. And those annual probabilities of occurrence are a more accurate way to refer to these different floods, that you've got that chance every year of that happening. We do talk about that in the newer modeling. We also have a couple more frequencies, the 25-year flood or the 4% annual chance flood, and something called the 100-year plus, which we'll touch on a little bit later. But when we're talking about that terminology, we try and stay from the 100-year flood, because people do tend to think that means, oh, it only floods every 100 years. So I had the big flood last year, I'm good for another 99 years. And that's not the way it works. It is a statistical analysis, and you've got a chance every year of having that really big flood. And some other terms that FEMA uses, they call that the base flood elevation, or BFE. In our state law, it's referred to the regional flood. And for insurance and lenders, they often call it the special flood hazard area. So that's SFHA, or the special flood hazard area, is going to be that zone A or AE area on the FEMA maps. And in general, I'll just call it the high flood risk area a lot of the time. So unfortunately, because the maps show that 100-year and we use that area for regulatory purposes and determining whether people are required to get flood insurance, people tend to have it's in the floodplain or it's out of the floodplain mentality. And part of what we want to point out today is that it's much more of a transition from lower risk to higher risk. It is not a nice sharp cliff like that you're really just in or out of the high risk area. And here's some depth grids that are produced in some of our flood map updates, the non-regulatory products. And this is a nice example showing that, okay, this red area here, that is the edge of the 100-year floodplain. But as you get in the floodplain, you'll see other areas are much deeper and have higher frequency risk. They might be the 10-year or even the 2-year floods. And this is really a useful map as it notes for hazard. Those working with emergency managers might use this information to look at where the roads are going to be underwater more, and helping to educate people that it's not an all or none situation. Or another way to look at this is a version of the same area, but looking at a 30-year period, because your typical mortgage is over a 30-year period. And that helps people to look at it a little bit broader perspective of, okay, yeah, I've got a 1% chance every year, but if I'm on the very edge of the 100-year floodplain, just barely in the 100-year floodplain, I've got a 26% chance of being flooded over a 30-year period. And that helps send a different message to people about their risk. But also this person who's in the 10-year floodplain or right on the edge of the 10-year floodplain, they've got a 96% chance of being flooded. So the mapping and the data that we have now, it's much more complete and covers a lot more scenarios than we've had in the past, and can help with the communication and helping folks at the local level with doing what they can to better protect their citizens, helping people to understand their risk better, and helping to prepare for when there is flooding, or helping to prioritize what areas do we want to do projects to reduce flood risk. Another aspect we need to think about is that the minimum floodplain regulations at 1%, it's based on today's conditions. It doesn't take into account future conditions and the trends that we're seeing in climate change, where we're seeing more of the rain coming in the intense storms, and that the flooding can be anytime between March and November, or heck, we had a fair amount of rain in February this year. So our times of flooding are not just mainly in the spring as people traditionally think of flooding periods. The other thing to consider is that even the information on the historical rain and precipitation patterns we've got better data over time. Many of the older maps were based on data from this technical paper 40, which came out in 1960 and was based on historical data in 1960. We have newer data that was released in 2013 that we call Atlas 14, and that includes a lot more information. And as I mentioned, the TP40, technical paper 40, it didn't have as many stations. It had a shorter record because it was based on information before 1960. But if you look at Atlas 14, it had a lot more stations. You've got an additional, basically 50 years of data that are included, and the elevations or the amount of precipitation, the inches of precipitation has increased over technical paper 40. It varies by different parts of the state how that's increased, but like here in the south, it shows it was 6 inches at this line here, and with the better data, more complete data, historical data, it's closer to 7 or 8 inches for that 100-year, that 1% probability 24-hour storm. So again, this is not even taking into consideration studies and trends of future conditions. This is just based on historical information. And this slide gives a couple examples of how much of a difference that made around in Minnesota, here in Minneapolis, the metro area, about a 30% plus increase. In Wisconsin, a location, it showed almost a 40% increase. Over in North Dakota, closer to 20%. And in South Dakota, about 24%. So this is not just Minnesota, but it applies to our neighboring states also. And where does this really make a difference in terms of the modeling that we use? For the modeling, and these are going to be some things that Ann's going to be talking about in a few minutes, but some of the methods that we use to come up with how much water is in the system are river gauges. And the river gauges, it doesn't affect it so much because the rivers reflect what's been happening over time. But there's models in some places around the state that are shown with these red areas, especially in the metro, fewer of the cities in the area, that those are the models where one of the input variables is that 24-hour 1% annual chance precip amount. So those are the models where updating with Atlas 14 can make a bigger difference. And Ann's going to take over here.
So our presentation is called Hydrology and Hydraulics for Non-Engineers. So now we're going to get into focusing on the question, what is hydrology? Hydrology is a term for the study of water's movement beneath the Earth's atmosphere. The hydrology of a stream can look at the estimation of the base flow in the stream and the flows in the stream during flood events and the frequency and duration of that flooding. The term flood discharge is a term for how much water is in a system and during a flood event, and it's usually in the terms of cubic feet per second. The flood frequency is a term that describes how often a water body floods, and it's usually represented as a % chance flood, like what Ceil was talking about earlier. There are various ways to study and predict hydrology of rivers and lakes. Some common methods include computer modeling, stream gauging, and using regression equations. Engineers and hydrologists use these different methods to predict how much water is in a stream or lake during a flood event and how often these flood events occur. So think about the water cycle that you probably learned about way back in the day in school. Hydrology is basically studying the different parts of this cycle and figuring out how often these things occur and how much. So using estimations of hydrology, we can predict how much precipitation gets onto the landscape, how much evapotranspiration there is, how much water soaks into the ground, which is infiltration, and then groundwater flow, and thus how much stream flow there will be in a system during a flood event and how often. When we're predicting flows in a stream, it's not just the area directly next to the stream that we're thinking about, it's the entire watershed. A watershed is an area of land that drains the rainfall and snowmelt into a specific water body. Watersheds can vary in size. A watershed for a small stream behind your house may be as small as just a couple of acres, whereas some watersheds are enormous in size, like the Lake Superior Basin or the Mississippi River watershed, which is in the magnitudes of millions of square miles. For the modeling that we do, we're usually talking about smaller subwatersheds that drain to single lakes or tributaries or rivers. The picture here shows a picture of Walter the watershed. In the picture, Walter the watershed is mostly undeveloped, and you can see there's just one small farm and looks like a black log cabin. And let's take a look at what happens when Walter gets more developed. So in the picture on the right, you can see there's a housing development that's moved in. There's a factory, a road, and some agriculture has moved into Walter's landscape. As the landscape changes in Walter's watershed, that will have an effect on how much water gets into the system, into the stream. And in general, more development means more runoff. Here's another example of that. If we look at an undeveloped lakeshore lot, there's a natural baseline amount of runoff that enters the lake from this property. And if you look at that same lot and put a small primitive cabin on it, and you leave most of the vegetation intact, the amount of water will increase slightly compared to the forested scenario. And then if you were to create a very large cabin with a lot of development and you see like some rock here and full landscaping, then the amount of water running into the lake will increase a lot more. And that's just because less water is soaking into the ground. So one way to describe the flow in a watershed in graphical terms is using something called a hydrograph. What exactly is a hydrograph? It's a graph of the runoff flow or discharge, which is shown on the y-axis here, over time, which is shown on the x-axis here. Scientists and engineers might talk about all the different parts of this hydrograph, but the important things that we want to talk about today are that there's the base flow, which is the area under the dotted line. That doesn't change with a storm event, but then as a storm event comes in, you'll see the discharge in the stream increasing rapidly until it hits its peak. And then as water works its way through the system, the discharge in the stream will fall off more gradually, as you can see on the hydrograph here. So you can look at hydrographs of many different rivers, streams, lakes, and it's just a way to describe the flow. So here's another example of a hydrograph, and now we're going to look at how it changes with land use. This is a hydrograph showing the flow in a watershed over a period of 45 hours. Now let's imagine that this watershed's a 200-acre forested watershed in a stream without any development. It takes some time for the water to start peaking, but it peaks at about 40 CFS at 15 hours or so, and then the discharge decreases over the next 12 hours back to the baseline. Now let's look at what happens when you change the land use in that watershed from forested to some type of urban development. The peak flow is going to be a lot higher. Now it's up at 210 CFS or so, and the peak usually comes sooner because the water is running off the landscape more rapidly than in a forested, undeveloped situation. So I think that's kind of enough about hydrographs. How do we estimate and predict or create these hydrographs using hydrology methods? There's some different methods that we use in rivers and water courses. We usually do statistics on river gauge data, and that's kind of the most accurate way to predict flows. We also do regression formulas in ungauged streams, and that's usually done in StreamStats. For lakes, we usually we can do different methods such as the Watershed-Drainage Area method, statistical methods, or the Shoreland method, and we'll talk about all of these later in the presentation. So this is the river gauges. On the left here, you see a picture of a river gauge that's measuring the flow in the Minnesota River at St. Peter. And in order to create the graph on the right, hydrologists use the gauge to measure the height of the river, and they go out at various times to measure how much flow is in the stream and how high the water levels are. So each of these green dots represents a sample point from the river gauge. A series of sample points on the stream can create what's called a staged discharge rating curve. And so as you can see, it's a lot of effort goes into these river gauges and getting the information out of the gauge for all of these different streams around Minnesota. Minnesota has quite a few river gauges. Both the DNR and the USGS have stream gauges in Minnesota, and the next slide will show a picture of just the DNR and MPCA's gauges in Minnesota. So there's actually a website called the DNR and MPCA Cooperative Stream Gauge page. And on that web page, you can click on any of these different points on the map, and this has a link to the page here. But within each of these points, there's a lot of information like the elevation of the stream currently, the flow in the stream currently, and you can look at the records of that information over the period of the gauge, over the lifetime of that gauge. So that's just some good information to know. If the period of record isn't long enough in the gauge, or there's no gauge on the river that we're studying, we'll often use something called StreamStats to get the hydrology information. StreamStats is an online web page that was created by the USGS that allows users to select a location on an ungauged stream site or a gauged stream site as well. Within StreamStats, a database that contains information for data collection stations, and a GIS program delineates a drainage area for the point that you click on. It usually does that using physical characteristics of the basin, such as land use and slope. And if you click on that location, get the drainage area, you can actually get the peak flows for that particular drainage area, which is shown here in red. So this shows the 1% chance annual flood flow, which is 340 CFS. And then these are the various exceedance intervals here. So these values are what we typically use for hydrology in ungauged streams. Like I said, it's not perfect, but sometimes it's the best that we can do. The next slide is going to show us that StreamStats gives us a range of values. So it works off of, I think, a 95% confidence interval, and the red line here shows the upper limit, which is called the 1% plus. And then the green line is showing the lower limit, 1% minus. And when we're doing flood mapping, we generally will map the 1% chance storm as well as the 1% plus storm in some of the newer mapped areas. And I think Ceil's going to take over now to talk about how to do some hydrology in lakes and basins.
Sure, thanks, Ann. So here's an example where one of the techniques we might use in an area, in a basin area, is, say we've got this basin. In this example, we've got Black Duck. And so we'll look at the amount of precipitation for that 100-year storm, and we'll add that amount of water to the lake directly. But then we've got all this drainage area that drains to that lake. And so we'll look at various parameters on the use of that watershed and soils and the slopes and how big that drainage area is, and then look at how much runoff we would expect in inches off of that area, and basically calculate the volume of water in that drainage area, and then calculate, okay, for this many acres of drainage area, if I pour that on top of this lake, how much more water does that add to the lake? And that's one of the methods we'll use to come up with what the 100-year or the other frequency flood elevations would be. That we'll use the ordinary high or the runout as a starting point, and then add that precip from that 1% annual chance storm. Another method that gets used occasionally is when we have a really good record of water levels going back many years, and we don't have any gaps in the data, especially in the years when we know we probably had higher or lower lake levels on that basin. And then they take the highest level for each year of record and plot it on this this graph paper here, which is in the log format there. And they do a best fit there, and then look at the 1% annual chance elevation based on those past historical readings. And another method that actually gets used fairly often in Minnesota is something that's called the Shoreland method. But a reminder, I think most of you know this, but just a quick reminder of what the ordinary high is first. That the ordinary high is what we use for the boundary of our public waters. It's defined in statute as where water's been for sufficient period of time to leave evidence on the landscape, basically the transition between aquatic and terrestrial vegetation. And that's something that we use for setting setbacks, and we use for some other methods. But the 1% annual chance flood elevations, usually higher unless there's some legal determination of what the ordinary high is by a judge. But in most cases, it's going to be a couple feet higher than the ordinary high. And here's the wording on what is the ordinary high. And then on streams, the ordinary high is defined as the top of the bank of the channel. And again, the flood elevation is usually higher than that bank, that it's higher than that ordinary high. So in our shoreland management regulations, starting back in over 50 years ago now, we've had the requirement of meeting low floor requirements in the shoreland district in addition to the floodplain district. And the shoreland rule says if you knew the flood elevation, you use your regulatory flood protection elevation. But then if we didn't know the flood elevation, we take the ordinary high or the highest known water level, whichever's higher, and we add 3 feet. And that's your low floor requirement. Now, if you compare our regulatory flood protection elevation, that includes a foot of freeboard, and our shoreland lowest floor, that 3 feet above the ordinary high. If you look at that, including a foot of freeboard, like the flood elevation does, we've argued that the flood elevation's actually 2 feet above the ordinary high or the highest known. So on our lakes in Minnesota, this is a method that FEMA has accepted when we don't have a more detailed study on a lake. And we do have actually a couple places that you can find the flood levels and the ordinary highs. You can go to our Lake Finder page. You can see the ordinary highs and the historical water levels if you choose the water level option in our Lake Finder page. And we now have our lake and flood elevations online viewer where we've got the ordinary high and the highest known are listed there also. If you want to know more about this method, we do have an info sheet. It does need some updating. Yes, those drawings are pretty old and not very fancy anymore. So that's on our list to get updated here in the future. And then we're back to Anne.
Yeah, so now that we've looked at hydrology and some ways to estimate the flows in rivers and lakes, let's move on to hydraulics. Hydraulics is the part of our modeling where we input the flows that we estimate when we study hydrology into a physical channel to estimate the water elevations. In hydraulic studies, we look at the shape of the land, and these models figure out how high and how wide the water will flow in that basin or channel. Some of the parameters that we use in hydraulic studies include the channel slope, the channel shape, restrictions such as bridges or culverts, and the roughness of the landscape. The hydraulic models that are commonly used include step backwater models such as HEC-RAS. And we try not to use HEC2, but we have to look at those old HEC2 models sometimes. There are other models that FEMA accepts to do floodplain modeling, which can be viewed on their website. A lot of data goes into building a hydraulic model. First, you need elevation data, and this can come in the form of physical survey data, which is usually the most accurate. We also use LiDAR data, and LiDAR data comes, you can see in this picture, there's an airplane. So a LiDAR plane flies over the land and it shoots down light to collect the LiDAR. After the LiDAR collect, GIS technicians process the data, and since they know the speed of light, they can calculate the elevation of the ground. And then they take all of those elevation points that they've calculated and mesh them together into a grid. And that grid is what's shown here on the right, which would be like a LiDAR DEM. This is a pretty new piece of LiDAR in Duluth, that 0.5 meter resolution. So all those points on the map there that you can see under the plane would be like 0.5 meter apart. And that's really good resolution for LiDAR. So in addition to using elevation data in our hydraulic models, we use aerial imagery, land use data, Manning's End data, and then information about bridges and culverts. Also, we'll take historical accounts of flooding in the area and take that into account for model calibration and that type of thing. So you might be wondering, what is Manning's N? Manning's N is a parameter that we use in hydraulic models that represents the surface roughness. So higher Manning's N values indicate rougher surfaces in a channel or floodplain, such as timber or weedy surfaces, and lower Manning's N values represent smooth surfaces, such as concrete. And this table here just has some examples of Manning's N values that you might see in our modeling. These values are important because if water flows over a rougher surface, it's not going to go as quickly and the water surface elevation will be higher. So that can have an impact on how much flooding and how high the water levels are going to be in any given stream. So the next slide here shows some examples of Manning's N values for different surfaces. There's concrete, which generally has a Manning's N value of 0.013. And then there's grass here down below. That's a nice big grassy channel with a Manning's N of 0.03, a little bit higher. And then the picture on the right shows heavy timber in the floodplain. This is the Baptism River up in northern Minnesota on a shore, and this is a higher Manning's N value of 0.1. So here's an example of spring versus fall conditions on a stream and how the Manning's N value can change. This is some pictures that I took of the Arrowhead State Trail, the Rat Root River, and the picture on the left shows some spring conditions, which, as you can see, there's less vegetation there, and the floodplains are going to have a smoother surface. And then on the right here, there's a picture of a fall condition, which there's all kinds of leafy, beautiful foliage, and that's going to have a lot rougher surface, which would cause slower movement of water in the floodplains and generally higher water surface elevations. And I think, Ceil, you had an example of when Manning's N made a difference in model calibration. I don't know if you want to run through that.
Yeah. Back, and I can't remember what year it was, but there was a fall a few years back where we had high water levels on the Minnesota River, and our crews were out there measuring the heights and getting the discharges, and they weren't matching the modeling that the Corps had for the river, and there was a little bit of back and forth on whether they had measured it correctly or not. And in the end, it did turn out that the difference that we were seeing higher levels for the conditions because there was that difference in growth in the fall, whereas the modeling was done based on spring flows. So it could definitely be seen in what they were measuring on the river during that fall flooding.
Next, we're going to look at the program that we kind of input all of this data into typically, called HEC-RAS. HEC-RAS is a computer program that was created by the Army Corps of Engineers in 1995. And it's the program that we most commonly use for the FEMA flood map modeling. This is a screenshot of the HEC-RAS model that I I pulled from the DNR's model download site of the Vermilion River. And the blue line is the stream center line. And the blue arrow down there at the bottom shows the direction of flow in the stream. So in this HEC-RAS model, the green lines that you see here are called cross sections, and the cross sections basically take a snapshot of the land under the line. And then you can see what's contained within that cross section here in the top right. All of the black dots are an elevation shot, and those elevations are usually a mix of LiDAR and survey data. Usually we'll get, for detailed studies, we'll get survey data in the channels and then use LiDAR on the overbanks. So in the past, we had to get survey crews to go out and get these cross sections for detailed studies. But now with LiDAR, it's a lot easier to get these cross sections. And Ceil gave me some estimates that for doing a physical survey of the land, it's about $10,000 per river mile, and for a detailed study, that's a lot of money. And now that we have LiDAR, it's reduced down to $300 per river mile. So that's a big cost savings. The gray marks here in this picture are structures. So it's usually either bridges or culverts. And then let's take a look at one of them here. So this gray line in plan view represents this culvert, which is a triple barrel round culvert, and the model contains information about these culverts, like the culvert inverts. It contains information about the material of the culverts with the Manning's N. It has information on the aprons and if they exist or not, and those types of things. And then the elevation of the roadway embankment over the crossing is shown in the red line there. HEC-RAS can model bridges too. The bottom picture here shows a cross section of the bridge in the model with two piers. So sometimes when you're looking at a flood map, you might say that the lines on the flood map don't really look correct. It doesn't look like as much water is getting through the road crossing as I know typically does. And so if you see that on an effective map, we can actually go into the model and take a look at what is contained within that structure and see if the model matches real life. And because some of our earlier Zone A modeling didn't actually include a lot of culverts or bridges, they just kind of assumed that the water would go over the roadway embankment. And some of the effective models that FEMA has are pretty old. Speaking of old models, so this is kind of the predecessor of HEC-RAS, HEC-2. And like I said, HEC-RAS was developed in 1995. HEC-2 was developed in 1968. And it's kind of the earlier generation. And we'll run into these models quite a bit when we're looking at effective models from the 1970s and 80s. And you can actually take the HEC-2 output and import it into HEC-RAS, but there are some challenges associated with doing this. Mainly, you can't always match up where things are geographically. There sometimes are some reference points, like as you can see in this output, it talks about which cross sections are aligned with which roadways and that type of thing. But when an engineer or hydrologist finds out they're going to be working with a HEC-2 model, usually you can hear some audible groaning or complaining because it's not that fun. And if for those of you that are old enough to remember like old stacks of computer cards, I think there's each row in the HEC-2 output represents one computer card. I'm not old enough to remember that, but
I do remember doing art projects with the cards that were left over from computer runs.
cards.
Yes.
I'd like to see some of those, Ceil. Next, we're going to talk about steady versus unsteady HEC-RAS modeling. So steady state modeling is a hydraulic modeling where the flow doesn't change with time. In those types of models, the discharge is constant at each cross section in the model. And usually in these models, we're using StreamStats for the hydrology inputs of the models. The numbers on the right are a screenshot from earlier when we were talking about StreamStats, and this kind of gives an example of a flow that would be put into a steady state model. So 340 CFS, you could input that in at the upstream end of the steady state model as the peak flow. So normally you're going to see steady state models done in Zone A areas for approximate FEMA modeling. And zone AE detailed models, we typically use unsteady state models. In unsteady state models, the flow changes over time. And this is our friend, the hydrograph that we talked about earlier. So in this hydrograph on the y-axis, you see the water surface elevation stage. And then on the x-axis, you see time. So as you can see, the water surface elevation in the cross-section is changing over time. Rises up, and then there's the peak, and then it falls off slowly as the storm passes through. So these flow curves, like I said, are called hydrographs. These hydrographs are typically generated in HEC-RAS if you don't use a river gauge. And usually you'll see unsteady state modeling in areas with storage areas, with dams, levees, areas with complicated backwater, or in detailed study areas, which are zone AE areas. We didn't want to do this presentation without talking about 1D modeling versus 2D modeling. All the models that we've looked at previously have been 1D models. In a one-dimensional model, the flow is one-directional, usually from upstream to downstream. And just like in the picture of the Vermilion River that we've been talking about earlier. And we'll typically use this type of modeling in most riverine systems. But in recent years, with technological advances in GIS processing and LiDAR capture, we've started to see more and more 2D modeling. 2D models can be done in HEC-RAS or other modeling programs. And there's a screenshot here on the right of a 2D model. 2D models consist of a group of cells that represent an elevation under each cell. And that group of cells is typically called a grid. In 2D models, you would apply a flow to the grid, and water is allowed to travel in any direction, depending on the elevations of those cells in the grid. So we usually see 2D models done in areas where there's more complex flow, like breakout flows or levees, or areas with a lot of storage, like series of wetlands or ponds. As you can kind of see in this picture, there's different storage areas on the landscape. It's not really a straightforward riverine system. So this is a good area to do a 2D model because the flow in the landscape isn't one-dimensional. Other hydraulic modeling programs that you might see include XP Swim, InfoWorks ICM, which is kind of a newer program that's coming out lately, and then HydroCAD. And these models are typically done in more urban areas because HEC-RAS doesn't generally model storm sewer well. And so that's kind of the gap that these models fill. Next, Ceil's going to talk about some of all of this stuff ties into the flood maps.
Right. Thanks, Ann.
Yep.
So Ann mentioned how we get the LiDAR, and then they use that geography, the lay of the land, and they do the modeling. They come out with cross sections, so they know the elevation that they want at those cross sections to represent that 1% annual chance flow. And we've got, especially in the newer counties where we've got the LiDAR, they would draw the boundaries of the floodplain using that better data on the ground also. So we've got an idea of how high it was going to get, and we have a better idea of where to draw the boundary of that floodplain. Now, at this point, we've just been talking about one run of the modeling, and long ago, FEMA recognized that not all parts of the floodplain have the same kind of risk. If you've been to some of our other trainings, we talk about how the floodplain gets divided into floodway versus flood fringe. But first, the engineers are going to run the model, just assuming that the water's flowing through that current system. Then they look at, oh, gee, the floodway is the area that we're going to be very restrictive. We want to show the area where it's deeper, faster flow, where it's more dangerous. And we don't want any obstructions from buildings. And we are going to be very careful about what we put in here because we know it's going to block water flow. So that's the area that we want to mark as the floodway. And then the rest of the floodplain is called the flood fringe. And it still will get wet, but it's generally the area where you've got less velocity and maybe shallower flows. and the community will usually be involved in marking what is the boundary that they think should be the floodway. Then the engineers will modify that cross-section that Ann was showing there and pretend that they'll simulate that they've got encroachment fill, that they've filled in part of that cross-section. And so that part of the cross-section is not available for the water to flow through. And if you obstruct part of your area where your water is going to go through, it does cause the water elevation to go up. And nationally, that limit is it can go up a foot. In Minnesota, we're limited to half a foot, and it can't increase flood damage potential. So if there's existing buildings already that are right next to the floodplain, you can't cause any rise when you're doing this modeling. You could only fill in areas where it's not affecting the flows through the system. So when they do this modeling, then they figure out, and sometimes I should mention that sometimes there's a little bit of adjustment that they might run it and find out the surcharge is too much. So then they have to adjust where that floodway is going to be until the floodway that is there and in the model doesn't cause too much of an increase in the flood levels. And then that revised run with that floodway shown is on our maps. On the older maps, that shows up as a crosshatch here. So there's that floodway there. And then the rest of the area in the 100-year floodplain is called the flood fringe. And while I'm looking at this map, I'll point out that the cross sections are on the maps. These cross sections that are in the models that Ann was showing, typical cross sections in a model there. On the newer map, the floodway is this red and blue crosshatched area, and the flood fringe is the more solid blue area. And the cross sections here, they're a little harder to read in this slide because when you zoom in on the FEMA interactive maps, they go and make those darn fonts of the information smaller on you. So then, if you want to know more about the data at those cross sections, you're going to want to look at your flood insurance study. And we have the flood insurance study and the map panels work together. That information you want to be using together. For the flood insurance study, that's where you're going to go to see more information about the cross sections, the floodway data table, and the profile. I'll show an example here in a couple slides. For the older maps that are about 1988 and earlier, they have two sets of map panels. One's the flood insurance rate map that we're used to seeing in more recent mapping, but they had a separate floodway map where they would show the cross sections and the data. So just if you're having trouble seeing the cross sections and you're looking at your firm, you may have an older map and it may be on this separate floodway map. Now in the newer mapping, it is all on one map panel. You've got the floodway and you've got the cross sections. So here's an example on the map panel. I zoomed into this area here so we can see some cross sections in this area along Perkins Creek in this example. So then we go to the flood insurance study, our handy flood insurance study. The older ones had that fun graphic. I'll go back a couple slides. Had that fun graphic here with the like 1950s era looking picture of people being rescued in a flood. And the very recent flood insurance studies look more like this. But if you go into that flood insurance study, there'll be the floodway data table for each of the streams that we have that detailed data. And we aren't today going to go into a lot of detail about the information in here. Just be aware that for each cross section, there's a row in this table, and there's information about the floodway and what the difference in the elevation is with or without the floodway mapped or modeled there. And we'll use these cross sections usually for our determining our regulatory flood protection elevation, because we'll get our base flood elevation from here, and it shows us that stage increase. That, as I mentioned, in Minnesota can't be more than 0.5 feet. But then if you want to know about other information that we've got, other supporting information, you go to the profile. In the older flood insurance studies, those were printed as an 11 by 17 kind of fold out page. And it's got that same cross section here, but it's got the thalweg, the river bottom, it's got the 10-year, the 50-year, 100-year, and the 500-year frequencies on here. It shows information on the road crossings and bridges and some stuff like that. So there's a lot of valuable information in here, but this is the place that you can go and get if you want to know the 10-year flood elevation for a site in a detailed study area. This is where you can find it. And I've just got a couple minutes left. I'm going to go through a couple resources really quickly. We cover these in other trainings, but we do have a site on our DNR page where you can go, and the FEMA hydraulic model download site. And these stream reaches that are the darker blue are where we've got a model available on the site. The gray reaches, either we haven't put the model there yet, or there isn't one available. But if it's gray, check with the DNR staff to see if we do have a model available. But you go here, you click on the stream, it will give you some information about that model, and you can download that model right here. And so you don't have to ask DNR staff to get it for you. For several years now, we've had these available at any time on this website. And in some of the situations, we may have multiple models for a reach, especially in some of these more complicated areas with detailed studies. And you can download those models there also. Another site I need to mention is our Lake and Flood Elevations online application. Here's the link to that site, and we had some helpful user hints in a July Water Talk 21 Water Talk article. Be aware that on lakes, we will have information on the flood levels if we have them for that lake. And you can send that over there to the side and see all that information, shows the source, the date, the type of study type. And then we also, in many of the lakes, have the ordinary high and the highest known listed if we have that in our records. For streams, we do have one of the layers is called the estimated 1% water surface elevations. These are basically those 1% elevations, or can be used as best available data for the base flood elevation. And those all coming from those models that Ann was talking about, those usually from a HEC-RAS model. And so we can use that as our estimated BFE there. And we're usually using the upstream of those unless we do more complicated determinations of where the site is more exactly and do prorating. We do have the newer mapped areas. The flood hazard zones are using the same symbology as the FEMA sites. And we do have in many of our counties that still have paper maps, we've got unmodernized layers here. So they're not the official layer, but they're really helpful for seeing the data. And we've got more and more areas where they still have paper maps, but we've got that better A-zone data is available. So we do make it available on our website. And 2 o'clock, right on time, I'm finishing here. So in my question slide, as we get toward this time of year, we just like to remind people for their wildflowers to go and clean that out right away. We try and leave them before we clean it up until it's at least 50 degrees consistently, and let the little critters that are sleeping in there, hibernating over the winter, that they survive that winter. And we'll go ahead and turn off the recording. And if people have other questions, you can go ahead and unmute yourself or put the question into the chat. And those of you who need to run off to other things, thanks for joining us today.